So in today's video, we're going to go ahead and introduce the notion of indefinite integrals. And so suppose we have a function capital F of x defined as the definite integral from a to x of f of t dt, right? Lowercase f of t dt, where t is just some arbitrary dummy variable. Then using the first fundamental theorem of calculus, we can determine that the derivative of capital F of x, so capital F prime of x right over here, is in fact going to be equal to lowercase f of x, right? So this is going to be equal to lowercase f of x. And so another way to kind of restate that is that capital F is the antiderivative of lowercase f. So f is the derivative of capital F, and capital F is the derivative of the antiderivative of lowercase f. And so with that in mind, we were able to determine the notion of the definite integral, and we defined it as the area under the curve, right? And so if you want to kind of think of the area under the curve of lowercase f of x, then you would need to actually find the antiderivative. You need to find capital F and then evaluate at those two endpoints in order to determine the area under the curve of lowercase f, right, over a defined interval. So this is where we got the notion of the definite integral. And if you actually evaluate this, then you should actually end up with some real number. We know that this is a real number because this is just an area under a curve, and so it can be just any arbitrary real number. And so another kind of notion that arises from the first fundamental theorem of calculus is the fact that the antiderivative or the integral is just the inverse operator of the derivative, right? I mean, the integral is the antiderivative, and so you can kind of think as the derivative and the integral kind of being inverse operations, right? They kind of cancel each other out in a sort of way. Not very rigorous, but that kind of does give you a sort of intuition. So we have the integral as the antiderivative operator, so it's the inverse derivative, if you will. And so this is where we can obtain the notion of the indefinite integral. And so another way to restate this exact kind of a relation right over here, capital F prime of x is equal to lowercase f of x, is by applying the indefinite integral operator. So this right over here is what we refer to as the indefinite integral, and notice that we omit the bounds of integration because now we're not really looking at the area under the curve over a particular interval. Now we're kind of just thinking about a more general form of the antiderivative. And so the indefinite integral operator applied to lowercase f of x with respect to x, so that's what kind of all this notation tells us, is just going to be equal to capital F of x and then plus c. And this plus c right over here is what we call a constant of integration. This is just a constant. It's just an arbitrary real number. And we're going to see why we actually end up with this in a moment. And so essentially what this tells us, what the indefinite integral tells us, is that a more general form of the antiderivative of f is just capital F of x, which is the antiderivative, plus c. And this plus c, we say it's the constant of integration. And the reason why we include it there is because if we were to apply the derivative of both to both sides, let's actually go ahead and do that. Let's apply the derivative with respect to x to both sides of this equation. So the derivative with respect to x of the indefinite integral of lowercase f of x dx is equal to the derivative with respect to x of capital F of x plus c. And so what happens when we apply the derivative? We mentioned that the derivative and the indefinite integral can kind of be thought of as inverse operators because the indefinite integral is just the antiderivative. So when you take the derivative of the antiderivative of a function, then you just end up with that function, right? So you can kind of think of these two canceling each other out. Not very rigorous, but it is kind of a good way to think about it intuitively. And so you do end up with lowercase f of x, right? Because you took the derivative of the antiderivative. And then that's going to be equal to what? So the derivative with respect to x of capital F, that's just going to be capital F prime of x. And then what's going to happen to this plus c? Well, keep in mind, this plus c, this c is just a member of R. It's just an arbitrary real number. And we know that the derivative of any constant is just going to be 0. So this will go off to 0. And then we just end up with this relation right over here, which we know is true because of this relation up here. We know that f is equal to capital F prime, or lowercase f is equal to capital F prime of x. And so essentially the reason why we include that constant of integration is because when you apply the derivative, it's just going to disappear. We know that lowercase f is the derivative of capital F, and so then we know that there could have been some constant. F could have included some constant of integration, and so that constant, regardless of what it was, it could be 0, it could be 100,000, it could be a negative number, regardless of what that constant was, that constant could have disappeared when we applied the derivative operator to obtain lowercase f of x, right? If that makes sense. So essentially, this is a more general way to define the antiderivative of a function. To define capital F of x is just to take the indefinite integral of lowercase f of x. And so this is where we kind of obtain this notion of the indefinite integral. And so while the definite integral yields a number, the indefinite integral yields a function, right? So this is going to yield some function, right? And the reason why it yields a function is because this function right over here is just the general function that defines the antiderivative of f. So if we want to obtain capital F of x, then the most accurate way to do it is just to take, or the most general and precise way to do it is just to take the indefinite integral of lowercase f of x. And so if you want to kind of even define it this way, you can say that capital F of x is just equal to the indefinite integral of lowercase f of x dx. And that's the most precise way that you can define a function as the antiderivative of another function. So here we can say, right over here, we can officially say that capital F is the antiderivative. So is the antiderivative of lowercase f, right? And when we evaluate this integral, we're going to end up with some constant of integration as well. And so that accounts for that constant. And so this is really what the antiderivative is. This is what the indefinite integral really is. This is just a very brief introduction to this, so if this doesn't make sense, that's all right. We will go into more examples and actually determining antiderivatives and learning these different rules for indefinite integrals. But for now, you just need to think of the indefinite integral as being the inverse derivative operator, and this constant of integration just being there in order to account for that constant that may have disappeared when we applied the derivative operator in order to end up with lowercase f of x.